Hello, my name is Nicolás Morabogue, and on behalf of Universidad San Francisco de Quito, my advisor, Dr. Pablo Torres, we would like to thank the Institute of Research and Development for Computational Methods in Engineering Science for the opportunity of presenting this paper. This paper is called Non-Linear Finite Element Models for Embedded Baseplate Connections. The main purpose of this research is to try to replicate the high theoretic response of an experimental program using nonlinear finite element analysis. The way this presentation is structured is in 4 parts. First, we will take a look at the connection geometry. Then, we will move on and see how the experimental program was developed and what results were obtained. Next, we will move on to the analytical model and we will see which parameters were taken into account, and finally we will move on to the analytical results. In this graph, we can see a general layout on how the analytical model was developed. First, we begin with the connection layout and its geometry. Then we move on to the finite element analysis model. We obtain the results and then we can calculate the hysteretic response of the connection. Baseplate connections are an integral part of steel moment frames. Their strength and stiffness have a direct influence in the probability of collapse of the system. In this type of connection, the steel column is directly embedded in the concrete footing. The steel column is directly supported over a baseplate that is partially embedded in the concrete footing. Additional stiffeners are added to the column to increase the panel show shear and also the stiffness of the bearing surface. In the following graphs, we can see the general layout of the connection. We can see a rectangular concrete footing that is composed of plain concrete that has no supplementary reinforcement. Supplementary reinforcement may or may not be added. In the experimental results, it was not considered. In this type of connections, 3 variables are of main interest: the embedded length, the column width, and the axial load. To gain a deeper insight in the connection behavior, we must first understand the load transfer mechanism. There are 3 main principal stresses: flexure, shear, and axial. Axial compression is transferred through direct bearing of the base plate and also due to friction in the column flanges. Tension behavior is similar to an anchor bolt. Flexure is transferred as a couple. There is an horizontal bearing component, also a vertical bearing component, and also the couple that is induced due to friction in the column flanges. And finally, there is a panel shear component. There is a diagonal compression strut that occurs in the steel component and also in the concrete pedestal. The experimental program was developed by David Greeley and Amit Gavinde. They developed a test matrix that may be considered as a factorial trio. The test matrix seeks to isolate 3 main variables: column width, embedment depth, and axial load. All the connections were subjected to cyclic loading, and also it is important to take into account that the column was made artificially strong to force the damage in the concrete pedestal. In this table, we can see how the test matrix was developed. There were 2 types of columns, a W14 and a W18 with different widths. There were also 2 types of axial loads, and finally there were 2 embedment depths. If we compare test number 1 and number 2, we can isolate the variable of the column width, because the axial load and the embedded depth is constant. If we isolate test number 1 and number 4, we can see the effect of the embedded depth. And if we isolate test number 3 and number 4, we can see the influence of the axial load. The width of the columns vary from 300 mm to 420 mm. The axial load range from 0 to 450 kilonewtons, and the embedded length vary from 500 mm millimeters to 750 millimeters. Load was applied cyclically, based on the SAC loading protocol. The load was applied in a quasi-statical manner, and axial load was held constant during the essay. Also, axial load was applied in such a way that there weren't second-order effects in the connections. In test number 1 and number 2, the load was applied until failure. These tests were the shallower embedded depths. In test number 3 and number 4, the load was applied until excessive deformation was achieved. These were the tests with higher embedded lengths. This connection may be idealized as a standing cantilever. Also, it's important to take into account that the loading protocol plays an important role in the connection response. This is due to the fact that the non-linearity in the connections occur mainly due to the effects of interactions between the two components. From the experimental analysis, we can see the following damage progression. We can see a linear response until 0.005 radians. Above this point, we can see a gradual non-linearity that is accompanied by the gaping of the flange pedestal and the concrete interface. Also, we can see that the non-linearity is accompanied by the strength and stiffness degradation, and it is presented as a pinching response in the connection. Also, the pinching response may be attributed to the effects of nonlinear interaction between the two elements. Concrete sprawling was observed past the 1% drift mark, and we can also say that the higher embedment depth leads to less strength degradation in the connection. The maximum or peak moment was observed between 1.5 and 5% drift. Interaction nonlinearity is characterized by cracks opening and closing in the direction of the loads. This leads to a slightly different response in each direction. In the tension flange, we can see significant gaping between the steel column and the concrete footing. And also, in the sides of the connection, we can see that there are flexural cracks and diagonal tension cracks. Later, we will see that the analytical model was able to replicate this type of failure. As this was stated before, the steel columns were made artificially strong to force the damage in the concrete pedestal. From test number 1 and number 2, the ones with the shallower embedment depth, the failure is controlled by the failure cone in the concrete pedestal in the tension side. As concrete begins to sprawl, the bearing mechanism is reduced and higher stresses appear in the failure cone. This precipitates the failure mechanism. From test number 3 and number 4, the ones with the higher embedment depth, failure occurs in a more gradual fashion. There is less strength degradation, and also the strength degradation is directly associated to the reduction of the bearing mechanism. From these graphs, we can see the general trends in the connection response. We can see that the main variable affecting the response is the embedment depth, followed by the column width, and finally the axial load in the connection. As stated before, the main objective of this paper is to try to replicate the hysterectic response of the connection. Now we're going to talk about the analytical model. The model was made in ABAQUS. ABAQUS is a general-purpose finite elements analysis software. In this model, we seek to replicate the hysterectic response of the connection. We try to achieve the same peak strength and follow the same strength and stiffness degradation trends that we can see from the experimental program. To achieve this, 3 types of nonlinearity were explicitly considered in the model: material nonlinearity, contact nonlinearity, or also interaction nonlinearity between the elements, and finally, geometric nonlinearity. To validate the analytical model, a sensitivity analysis was performed to see the sensibility of various model parameters in the response. It is important to note that in the experimental results, the steel column remained essentially elastic, so in the analytical model, the material nonlinearity was applied only to the concrete. 4 models were developed to try to replicate test number 1, number 2, number 3, and number 4. In the model, solid continuous hexagonal elements were used. These are called in ABAQUS C3D8R elements. These correspond to 8 node elements with reduced integration and control type hourglass. The order of integration was selected as linear. The element type and the geometric order of the elements responds to a balance between precision and analysis time. Since hexaedral elements were used, the meshing was achieved using a manual procedure. And mesh sensitivity was incorporated in parts where the non-linearity was expected. In this graph, we can see the general layout of the mesh of one model, and we can also see the parameters that were used in the ABAQUS model. For the analytical model, we tried to use the same loading protocol that was reported in the experimental results. The idea was to try to have the same response. As we can see in the reported loading protocol, there are some parts that are discontinuous. This way, we can obtain a better match of the hysteretic response of the connection. When it comes to the model material definition, for the steel, it was modeled using a linear elastic material element, and this is consistent with experimental results. An elastic modulus of 29,000 KSI was used with a Poisson ratio of 0.30. For the concrete, we used a continuous model based in plasticity with damage. This type of model is called Inabacus concrete damage plasticity model and is a formulation that was proposed originally by Lee and Fembes in 1998. This model considers distributing cracking along the continuum. It is also known as the smear crack model. The model assumes two principal failure mechanisms: tension cracking and concrete crushing. For the model definition, uniaxial material behavior was considered, and specific coefficients of the concrete damage plasticity model were taken into account to develop the failure surface and the flow potential of the plasticity model. In this type of model, the flow potential is characterized as a Drucker-Parker hyperbolic function. The variables that control this parameter is the dilatancy angle, the maximum tension stresses, and the eccentricity. The yield surface of the model is a loop linear function with modifications proposed by Lee and Fembes. The yield surface depends on the maximum effective stresses, the ratio of the equivalence compression stresses, and the ratio of the second invariable of the maximum meridian stresses in tension. Also, in this model, the cyclic response of the material is represented through damage parameters. If damage parameters are not taken into account, the material behaves similar as a plastic model. For this type of connections, taking into account that the non-linearity is mainly a non-linearity due to interaction, damage parameters were not taken into account. For uniaxial material behavior, in compression we used the Popovic's model, and in tension we used the fifth model code. And finally, when it comes to the concrete damage plasticity model, the direction of the cracks can be inferred as parallel to the direction of the strain of the principal strain in the places where the plastic strain is greater than 0. ABAQUS recommends using the plastic equivalent strains to see the cracks directions. In these graphs, we can see a general overview of how the material model is considered. In the left, we have the uniaxial material behavior, and on the right we can see the yield surface, and also how in the uniaxial material behavior the damage parameter affect the stiffness during the cyclic response. In this graph, I am presenting the material model definition in ABAQUS and also the parameters that were used in the final model. Contact definition is a very integral part of the nonlinear behavior of this connection. Two types of contacts were considered: tangential and normal contact. For the normal contact, we use a hard contact formulation, And for the tangential formulation, we use a frictional formulation with a constant penalty and a coefficient of 0.445. As stated before, this definition is really important because it determines the gaping between the elements and also the opening and closing of the cracks in the material model. From this graph, we can see the general results. As stated before, the main objective was to try to replicate the analytical behavior of the hysteretic response of the connection. We can see a really good match between the experimental results and the analytical results. This trend can also be observed from the monotonic envelopes of the connection. We can see a really close match between the stiffness and strength of the connection, and we can also see that we were able to achieve similar strength and stiffness degradation during the hysteretic response. There is a slight discrepancy in the peak moments, especially in the later parts of the response. This may be due to the material models used in the analysis. For the results, I am focusing on test number 1 due to time constraint. Here we can see the force displacement envelope and also the hysteretic envelope, and we can see that the match is really good. I am presenting here the graphs corresponding to 1% drift, and we can see that the column is mainly elastic. We can see a little plastic strain in the concrete, but is localized. And also we can see in the table that the type of damage that was reported in the real connection is similar at the one that is modeled in ABAQUS. These are the photos of the damage in the connection. We will use the photos to qualitatively evaluate the response in ABAQUS. Here we can see the results for a drift range between 3 and 4%. We can see the sprawling of the concrete in the compression. We can also see the diagonal cracks, and we can see the flexural cracks in the connection. In general, a good match and a good agreement with the experimental result. In these graphs, we can see the plastic strain in the concrete. As stated before, this can be a good measure of the cracks in the material. Here, we can see the interaction effects between the different materials. We can see the gaping that is formed between the tension flange of the column, and also we can see the gaping that occurred in the base plate. Also, we can perceive the concrete failure cone. Here we are presenting a graph with the von Mises stresses in the steel column. We can see that the column remains mainly elastic. Additionally, we can perceive how the moment is concentrated near the concrete face pedestal. Here we can see the results from test number 2, test number 3, test number 4, and also I am gonna show you a video showing the cyclic response that was modeled in ABAQUS. In this video, we can see the cyclic response of the connection. In the upper left and middle image, we can see the steel column von Mises stresses. In the upper right and bottom images, we can see the plastic equivalent stress. These are related to the concrete cracking. We can also appreciate how the steel columns remain essentially elastic and how the moment is distributed near the top face of the concrete pedestal. And finally, we can also perceive the failure mechanisms that occur in the connection and the nonlinear interaction effects between the different types of elements. Also, in the lower depth image, we can see the bulging effects that occur in the top surface of the concrete pedestal. Finally, we will take a look at the sensitivity analysis. Here we can see how the angle of dilatancy affects the connection response. As we increase the angle, we increase the connection peak strength. We found that an angle of 31 was good enough to achieve the experimental results. Next, we can see how frictions play an important role in the connection response. If we remove friction from the interaction effects, we can see that the decreased moment from the couple decrease the overall connection response. So friction is a really important part. Next, we can see the effects of the geometric nonlinearity in the connection. As we can see from the graph, geometric nonlinearity plays little to no role in the hysteretic response. And finally, we can see how viscosity affects the connection response. Viscosity will be directly related to the yield surface. We can see that the overall trend in the connection response is really well characterized. We can see that we have a linear elastic branch that exhibits a similar trend at the experimental program. Also, the overall hysteretic behavior is well matched. Additionally, we were able to characterize the strength and stiffness degradation in the connection. And finally, we were able to replicate the gaping response and the failure mechanism in the connections. This is the end of the presentation. I would like to thank everyone for listening. Thank you.